Here we are with homework 3 in ME370, and here's the solution. Well, we'll start out with here's the problem. Here are the problems. Okay, so we have this pipe, schedule 80. In this case, it's a 10-inch nominal diameter that actually has an outside diameter of 10.75 inches and a thickness of 0.59 inches, and it's subjected to pressure. Right, so it has inside pressure of 2,800 psi, and it's 72 inches tall by 48 inches here in the X direction, labeled B here, and then an additional 60 inches in the Z direction right there. So it comes up like 6 feet, 4 feet, and then 5 feet, like coming up there. And the forces are all kind of in the this is a negative direction here. So the X is in this direction right there of 10,000 pounds, like 5 tons. And the Y direction is down 12,000 pounds or 6 tons. And then we have 7,500 in the Z direction pulling onto there. We want to determine the principal stresses, all 3 of them, and the absolute maximum shear stress at a point on the inside of the pipe at H, right? So we're going to be at H, but be on the inside surface of the pipe. And we're going to include transverse shear. We're going to include all of them, but we're going to use transverse shear. We're going to do an estimate of it. So we're going to use the simple maximum transverse shear, but we're going to use the same equation for the inside of the pipe that would be true on the outside of the pipe. So that's a little bit of an estimation that's going to happen here. And we wanted to make sure we draw the fully labeled 3D Mohr circle as part of the solution. We also have problem 2, where we're going to now use, so up here we're going to use the thick-walled equations for the pressure vessel, and in part 2 we're just going to simply recalculate for the using the thin-walled approximation, and then discuss whether that's appropriate or not. So here is the problem right there written out. I didn't do a great job on my sketch right there. I could have done better, but better than most, right? So here's all the givens and the find. First thing I do is I get some geometry out of the way. So I get the inside diameter, right, which is the outside diameter minus 2 times the thickness. And then I get the outside radius and the inside radius, because I'm going to need that for the equations that we use for the thick-walled. I get the area. A common thing to do is a mistake to make is to square it out here. You need to square them individually, right? And the same thing here. Use this to the 4th and that to the 4th when you get to the area moment of inertia. Oh, and it wouldn't be a bad idea up here in the geometry part to take the thickness, I need more coffee, and divide it by one of the radiating. It doesn't really matter which one, just to double check. And we see oh, look at that, it's actually pretty close to that thin-walled transition of 0.1, right? The suggestion to be of the thickness 1/10 of the radius is when you make the decision whether you'd be thin-walled or thick-walled. It's larger than 0.1, so, and I already told you to use the thick-walled anyway. So, okay, so here we are. Here's our free body diagrams to get the reaction moments. And I think I didn't bother getting them in the plane where it didn't matter, right? So we were looking for H. We're looking for point H, which on this diagram would be like right here. So this is the moment that we want to get. That's the one. This is the moment that's going to cause bending right there for us. We put the loads in. Make sure you fully label this all the way and go through the same. Go through the routine and some of the forces, so you can get the reaction right here in the X direction, get the reaction in the Y direction, and then get the sum of the moments about the Z axis, right, coming out of the page. So we're going right around there, and we're able to get that reaction. Noteworthy that these are in competition with each other, right? So this 10,000 wants to go clockwise. This 12,000 wants to go counterclockwise. We guessed that the answer would be a counterclockwise, and sure enough, we got a positive answer, so it was counterclockwise. And while we're here, we might notice that if this is the location of H right there, then this is going to cause compression. But let's wait for a second. We'll look at the stump. The same thing here, where we're going to take the loads that are applied to it. Both of these are trying to go clockwise, right? So this one has to go counterclockwise, and this one is about the long axis, so this is the torque. So here, this right here, this reaction right there. A lot of times I'll go T right there when I make this statement already, but anyway, we know that's the torque. So those are the loads. I think I have the next page. I do the, yes I do. I put this in there, and I didn't bother calculating this one, so I didn't need it. But here's actually where the stress element is going to be for this problem. And we can see that this is the equivalent moment, right, as opposed to the reaction moment. And this is opposite from the reaction moment. But we can see that that is going to cause compression. We can also see that this axial load on here going downwards is going to cause compression. And we can see here is the shearing moment, torque right there, right? And so it's going to go across to that face. And then here is the load that's going to cause transverse shear, and it's going that way. So the transverse shear is in the opposite direction from the applied torque onto the thing. So we move on to the stresses. I start with the axial. And the axial is going to be caused by that 12,000 coming downwards, and it is going to be in compression. And it's not a large value when you're using KSI. Then I go for bending, which I already mentioned was 144,000 was the moment that causes bending. But noteworthy, we're looking at an element that's on the inside surface. So that a lot of times that would be C, which would mean the farthest point away from the neutral axis. In this case, it's not the farthest point. We might even use, sometimes we use y in this equation, but that's only if it's oriented with the y-axis. So I didn't use y, I decided to use ri. And this is compression right here, so we get like 2.826. The next, I decided to go hoop. I don't know why I went to go hoop next, but there it is. Hoop, there it is. I feel bad about that. Sorry about that. Anyway, here's the equation, and notably that this is a variable, and so this is the radius at which you're taking the hoop stress for the thick-walled equation. So there's 2.8. I went ahead and used KSI. 2,800 psi is the internal pressure, but this is the location. See this on the inside surface, and that's going to give us 24.19 ksi, and this is in tension, right? That's the hoop, like, you know, it's trying to make the thing bigger, right? So it's this is also called the tangential stress. Here's the longitudinal, and this one wants to make the thing longer, right? It's kind of stretching the thing up, so it too is in tension. And you know, you can note that this right here is the same thing as that right there, right? All right, so here's some shears. We do torsion right there. Okay, once again, that's the torque that's being placed onto the thing. That's this guy, and we use the inside radius again, because that's, you know, the exact location for us. And then the transverse shear, this is an approximation, so I put a little approximately equal to. And for a hollow cylinder, that's, or, you know, circle within a circle, that's 2 times V over A is where the maximum is. And I said that we had 7,500 was the force. This guy is the one that causes a shear here and here, whereas this force, 10,000, causes shear here and there, or the maximum right there causes. All right. And okay, so now we want to like get all these together, combine everything. And so this is looking, let's see, take a look at the original one. This is the YZ plane that we're looking at. But we're like Superman, so we could see through the outside of the pipe. But this is that's the orientation, and we could see that we have longitudinal is trying to make it longer. It's in tension. Bending is crushing it. It's compression. Axial is compression, right? So we could subtract them out. So this is what the sum total of the stresses are in the y direction. In the z direction, it's only hoop, so there it is. And we know in the x direction, which is really kind of coming out of the page at us, that's going to be equal to the pressure, right? Because it's on the inside surface, and it's compression because it's trying to squeeze the little cube. And I think, I don't know if I wrote the thing out here. That's weird. I didn't write the thing out. I must have written it somewhere. No, there it is. Okay, sorry. Here's the shear. I'm combining it, and this is in the YZ. So on here, I put in the Y face in the Z direction, and the torque was, let's say, coming that way across the face, whereas the transverse was coming that way. So they're opposite from each other, so they subtract that little bit, and we get this 8.624. And so here is like sort of a summary element. And now we want to do a Mohr circle on this. Okay, so in Mohr circle, we want to first plot the faces, right? So I plotted this point right there is this face. There's the normal stress, and here's the shear stress. So there's the normal stress and shear stress right there. And this is going clockwise, which the convention is that's the upper level of the shear right there. And then I'm going to plot this face right there. So we have tension of 7.237, and then they have the same shear. So that's going to be down here, see? And okay, so I figure out what the center of it is. And by the way, my graph, I had a mistake earlier that I've fixed here, but the graph was pretty close, but now it's not exact. But I did get it to scale at one point. And anyways, here's the center, or approximately the center. And then here is the radius, and I took this one to be the radius. So I had this leg right here is C minus this. So I took the 15.71 over right here, and I subtracted out the 7.237 right there to get that leg. And then the vertical leg is, of course, the shear. So I get 12.09 to get the principal stress here, C plus R. To get the principal stress here, it's going to be C minus R. And then we know that this one is the third principal stress, and it's in compression because it's going on the face, and there's no shears over there, so we don't need to do anything with that. It would be a complicated Mohr circle if it was anything more than that. We'd probably end up using eigenvalues to get the principal stresses. But anyway, here's the absolute maximum shear. Is sigma 1 minus sigma 3, but in this case, sigma 3 is negative, right? So I got to end up adding those, and so that's the answer right there. 15.3 KSI. All of that work for that. And let me take a look at how long this was. Of 13 minutes. Maybe I want to continue and make a separate video, but I did want to go to the finite element analysis here. Let's see. It won't come. It's not coming up. I think the graphics is too much for my computer right now. I'll move this over to the side. I'll move him over to the side. Move him over. Okay, so maybe it'll come up. Why aren't you coming up? All right, so we have this guy. He's problem 3. Let me see. No, there you go. Wow, he's just being a pain in the ass. Okay, so here is the model I've made of that problem that we just saw. I put an end cap onto the end of it. I don't know if that was necessary. We could actually, this is just a demonstration of doing this. I'm not sure that we would ever do a problem like this, in a real world, because you could do it by hand, right? So, but this is sort of just a confirmation. So one of the issues with FEA, you want to make sure you don't want to misuse elements, and there needs to be a certain number of elements through a thin thing. And when there's not, there's actually elements, called plate elements, that work way better for this type of operation. But we're going to go ahead and use the solid elements that are in SolidWorks simulation. And I'll show you the mesh that I have. So I'll go show mesh. I did increase some meshing around this location, and my modeling approach, by the way, was to model a little bit of the part below the area where I care about, because as you get closer to where the boundary conditions are, you could potentially get incorrect kind of treatment. So I kind of like move them away a little bit away from that. We could go into why that would be. So anyway, I also put split lines in here so that I could find a specific spot. So like right here is point H, but I could go into the inside part of this and zoom in, and this is the stress element that we're actually looking for on the inside of that piece. All right, so I think the stresses I'm showing initially here, all right, after performing this, are called von Mises stress, and we'll learn more about that in Chapter 5 of Shigley. But for the time being, just think of it as a really useful single, always positive value to kind of assess the thing. It's something that's very good, useful for comparing to the material strengths that you get from an axial pull test. Okay, so I want to actually look at some values here. So in the y direction, so let's take a look at the normal stresses in the y direction. Yeah, I'm just going to leave the scale I have here. You'll notice I have a nice scale from 0 to 50 counting by 5s. Isn't that pretty? And let's see, I want to double check that I'm getting, because the orientation, it can get a little lost as we try to balance it. I'm going to pick that point, and then I'm going to zoom in down here, and hovering, I'm picking that point. So I'm going to use the probe thing here, and I see it disappears, but we got that right there. All right, so we get 7.18 KSI, and let's look back and see what we had in our 7.18 in the y direction. Oh, here you go, 7.237. So that's actually not so bad in terms of a comparison, 7.18. And I meant to say this a second ago, but short attention span, I forgot. Okay, one test we should look for is how many elements there are through the thickness of a part, right? And this is only, because we're making like, I can think of them as triangles, but I guess they're tetrahedral stress elements. We kind of have two, but not really. I wouldn't think of them as having two elements through the thickness. It'd be nice to have multiple elements through the thickness of this, but the modern stress element is formulated to kind of handle things a lot better than old ones used to. Cubes used to be the best, and tetrahedrons were too stiff, and you wanted to make everything nice and symmetric. You didn't want a cube that would look like a tissue box. You wanted it to look more like just a regular cube, right? So the longer and narrower and skew that you have are worse results. It would be nice, evenly distributed kind of things would be look good. I don't necessarily mean evenly distributed up here. Don't need to teach you FEA right now, but we'll get to that. In any case, this was a pretty good result, but we might want to change the mesh in the location and kind of see what the effect is. See if we got closer, but this is actually pretty acceptable, I think. Now in this direction, I could change this to cylindrical coordinates, but this one is actually aligned with the Z, right? So we could find the stresses in the Z direction. So we'll change what we're plotting here to the Z direction, normal stresses in the Z direction. And then use my plot tools and go to the probe again. And I do believe it's going to be right there. And I see I got 24.14. And compare that to, and that should be equal to, 24.19. Wow, that's pretty good, actually. It's like really good. It's like scary good. If we wanted to, we could also take a look at the principal stresses, right? So we have that capability there. That's one of the options in the results here. So we edit definition, and we'll make first principal stress. You can see this is first principal stress right there. And then we can go probe again and pick that out. See 27.72, and what did we get? Wow, that's pretty darn good. 27.8, and so that's pretty good. Unfortunately, I don't think there's a way to get absolute maximum shear out of SOLIDWORKS simulation. I know in ANSYS that one of the outputs is something called Tresca, which is another name for the maximum shear stress theory stress, which is the absolute maximum shear. But this is these are pretty good confirming results. Now, the last part of this, I want to do problem 2, and then maybe make a separate video for problem 3. I said I wanted you to compare the thick-walled and the thin-walled hoop stress, just to see what the difference was going to be. Now, the equation we're going to use for the thin-walled should be the maximum, because it is on the inside surface, and Shigley has an equation for the hoop stress on the inside, and he puts a maximum like right there. And so we take the inside diameter and add N1 thickness, and then multiply by the pressure divided by 2. We get 24.54. And then the thick one, which we'll call, we got 24.19. That's only like 1.5% difference. That's not bad. It's not too bad. And even though that we are up just above 0.1, is 1.45% acceptable. Now, this is a matter of opinion. I mean, in judgment or experience, and say, well, the thing is, for my judgment, and this is not any reason that you would necessarily know this, but if you ever go to a pressure vessel that has, especially an analog gauge, just look at the gauge and read the pressure. Tell me how accurate that pressure is. Well, there's something called parallax error, right? Where if you're looking straight at it, it looks like one thing, but if you kind of go to the side or into the side anyway, you can kind of change with the answers just by looking kind of from the side of the needle, right? Because the needle's not touching, right, or of the back plate of the thing. They call that parallax error. But even if it's a digital pressure readout, right, and it's got a, like some pressure transducer, and you're reading the display. That thing can fluctuate. You'll notice it. It depends on what the thing's full of. So you have to how accurate, how certain are you of the number on the pressure gauge, and then kind of compare that to what our results are. I say it's acceptable, but then again, I'm a marine engineer, not a lab technician. So I don't know. I think it's pretty good, actually. So I'm going to make a separate video for the solution to the other problem. Hopefully somebody found this useful. Somebody did. Maybe. It's too long. Talk too much.